Okay. Resuming, let me repeat what I said here about this equation. The translational kinetic energy, this first term, includes translational kinetic energy for the chassis, the frame of the car, which is W, plus 3 wheels, all of which have a mass center velocity V0. So that is translational kinetic energy of the car plus 3 wheels. The wheels, in addition, but not the car itself, have 3 of them. Each one has 1/2 I about G for the disk times omega squared. Okay? Now, omega is still related to V0 over R like that. And that's how we compute kinetic energy at time 1 in terms of V0. Right here. Okay? 1/2, the total weight, that's the weight plus 3 wheels, over G, times V0 squared plus 3/24, having done a little arithmetic up there. The weight of each wheel over G times V0 squared. So there's only one unknown in there. Well, it's not unknown. There's one parameter of speed. That's V0. We've used kinematics to eliminate omega. Okay. Remember, the car is going to hit the ground. The front end is going to hit the ground, and it's going to skid along with frictional force F acting from the ground. So free body diagram of that car. Well, let's see. I don't have a wheel on the front. It's moving in that direction. And there's a friction force here. Also a normal force. In front and in rear, but they're not doing any work. Since the direction of the displacement and the velocity vector is horizontal, the only force that does work is F. And it's doing negative work. You see, it's pointed in the direction opposite to the velocity vector. It's tending to slow the car down, reduce kinetic energy. That all means it's doing negative work. So the work done is minus F, the magnitude of the friction force, times D, the distance it slides, which is what we're trying to compute. And I pointed out that U12 is F, is negative, and minus F times D, the work done between 1 and 2, is minus the kinetic energy at time 1, with KE2 being 0. And from that, we find distance D. It comes out to be a positive distance. It's going to have units of length. WT plus 3/12 WW, WT being the weight of the car plus 3 wheels, WW being the weight of each wheel, over 2GF, F being the friction, V0 squared. Let's check our units. We got force on top. We got velocity squared, length squared over time squared. We got down here G, which is length over time squared, and we got force. So the force cancels. The time squareds cancel. The length cancels with one of those, and we're left with length, which is the right units for D. It's a good idea to check your units. Okay. So we saw several examples of work energy. I think we'll probably have a chance to work some more, but I want to go ahead and talk about impulse momentum. Remember, the methods that we're going to talk about for handling all these dynamics problems are Newton's second law, F equals ma, and some of the moments is I alpha, which allows us to solve for acceleration. Work energy allows you to solve for the final conditions of velocity. And impulse momentum allows you to solve for final conditions of velocity under other circumstances. The impulse momentum equation says that the impulse, I, is the change in linear momentum. Recall, the linear momentum, P, is mass times velocity vector. Okay? For a rigid body, it's mass times V sub G. Okay, but for a particle, it's just mass times v. The impulse is the integral of the force that acts over time. So it's got units of force times time, pound seconds or Newton seconds. Momentum has units of mass times velocity. impulse momentum is useful to you as a tool. This is not to say that it only applies then. Impulse momentum is a very general principle. It always applies, but it's a useful analytical tool, especially when impacts occur. Whenever you have particle A or rigid body A bumping into something else, whether it be another particle or rigid body or a ground plane, we call that an impact. And when that happens, we almost always have to apply impulse momentum somehow. It's also useful when the force is a known function of time rather than position. You notice in the previous problem where we had the force there was a constant. If we were told that the rocket motor fires for while the sled is fired while the sled is traveling 100 meters down the track, then we're able to compute from that the thrust in that rocket engine and the 100 meters of travel, we're able to compute work. That'd be a clue that work energy would be the useful tool to use. If we know that the rocket motor fires for 3 seconds while the sled is traveling down the track, then we can't calculate work because we don't know the distance it travels, but we can calculate impulse, which is force times time, the thrust times the 3 seconds it fires. So whenever we know the force as a function of time, then we can compute the impulse, and it's sometimes a useful tool in those cases too, although by far the most use you'll make of it will be in working problems involving impact. Those are the most, that's the kind of problems you're going to see on the EIT in my expectation. Let's talk about a pretty general case of impact. I don't think you'll see anything that is this general, but I want to go through it, and then we'll look at the simpler case of direct central impact. This is a general case of, two billiard balls striking at an angle. One of them has velocity A1. The one means time 1. The other one has velocity B1 at time 1. They come together, and A1 goes off here and B1 goes off here in directions that we can determine by application of impulse momentum equations. At time 2, the velocity of A is denoted VA sub 2. The velocity vector of B is denoted VB sub 2. A doesn't pass through B, you'll notice. The only forces that act in this interaction are internal. Okay, that means that if we draw a free body diagram of A during impact, we have a big force, which we might call F, that acts, and on B, the same force acts. So if we were looking at A or looking at B, we would have to include this force F, and it causes an impulse on A and an impulse on B that are equal and opposite, this being a vector, equal and opposite vectors. But if we consider particles A and B together as a system, that force is internal to the system of particles, and there's no impulse due to F on the system. So if we have a collision of two particles, and there are no impulsive forces that act, we can say that the impulse equals a change in momentum is an equation that tells us the final momentum of the system equals the initial momentum, or linear momentum is conserved. Conserved means constant. Linear momentum is not always conserved. Sometimes there's some impulse, non-zero impulse, but for this particular system, it's conserved. I ought to say what is meant by an impulsive force. An impulsive force is a force that dominates the behavior of the system during a short period of time. If you consider a pitcher in baseball throwing a pitch that travels 90 feet, and during the time of its travel, it's affected by aerodynamic resistance, which tends to slow it down, and if he's put some spin on it, it tends to make it curve maybe, and by gravity, which makes it fall. Those are the forces that influence the motion of the ball during that period of time. Now those forces still act when the batter, if he's lucky enough, hits the ball. During the time the bat is in contact with the ball, we still have some aerodynamic resistance. We still have some gravity. We still have some drag. But by far the most important force that acts is the force between the bat and the ball, because it's 100 times, 1,000 times as big as the others for that short period of time. So we call that force an impulsive force, which means we are usually justified in throwing out the effects of the of aerodynamic resistance and gravity and any spin that might happen. We throw out all those effects, and during the time of impact, we say the force of the bat on the ball is the only important force because it's an impulsive force. And the entire motion of the ball during the time it's in contact with the bat is governed entirely by that big force that acts from the bat. So that's what we mean when we say an impulsive force. Now, not all forces, it's usually true that in impact, the force of impact is an impulsive force, and it usually dominates the collision of the two particles. It's the only force you need to consider during a collision, but you can't say that in general. It's just a very common scenario. In the case of two billiard balls colliding on a table, or maybe two automobiles impacting each other, if impact is a very short period of time and the speeds are high, such that the forces are very high, then it's a good approximation to say that the forces are impulsive, and during that collision you forget about any other forces that might be the case. Now, there are sometimes other forces besides between the two objects. Consider a cannon. Let's see. I want to make another page of notes here that I'll number 56B. Okay. Consider a cannon sitting on a horizontal surface. Guess I'm not much at drawing cannons. Okay, but here we got a cannon. It's resting on the ground. I'm going to leave the ground out, and I'm going to draw a free body diagram of this cannon. There's some force from the ground, which I'll call R. There's a weight of the cannon, which I'll call W. And as the cannon fires, there's going to be a force between it and the projectile that is pretty large. It accelerates that projectile to a pretty high speed in a pretty short period of time. Notice that if I show that force here as acting in this direction on the cannon and that direction on the force, on the projectile, if it's an impulsive force, if it's very large, what happens to this force down here, R? Well, either the cannon is pushed into the ground, which it is, but if the ground is pretty rigid, if it's sitting on a concrete parking lot, you would expect that this high force is going to cause a pretty big force here. Maybe you learn at Fort Hood, don't put your foot under the cannon when it fires. I expect you to learn that pretty quickly, because the point I'm making is this force may be an impulsive force as well as this force. So you may have impulsive reactions to consider. But this is what we mean by an impulsive force, a force that acts, that's very large and dominates the problem in a short period of time. If you have a reaction that prevents the cannon from going anywhere, then the reaction is very likely to be an impulsive force as well. Okay, back to this thought here. Whenever we don't have any impulse, in other words, if we don't have an impulsive reaction, like in the case of the cannon, two balls coming together, the external impulse is 0, and we can write the momentum at time 2, mass of A, I need an A on here, times velocity of A at time 2 plus mass of B times velocity of B at time 2, they aren't necessarily the same, minus the mass of A times the velocity of A at time 1 plus the mass of B times the velocity of B at time 1, is a statement that, if I put one of these on the other side of the equation, the final linear momentum is equal to the initial linear momentum. Our linear momentum for that system is conserved. Do you think linear momentum for the cannon itself is going to be conserved? Probably not, because you got an impulsive reaction on it. Well, you have to be careful in those cases anyway. This is true whether the particles are perfectly elastic spheres, like billiard balls, which are almost perfectly elastic, or whether there's something like a blob of putty that are going to stick together. Okay, we haven't said anything about what they're made of or how they behave. They may strike and rebound, or they may strike and stick together and move off as one. How do we address that? we describe the nature of an impact between two objects with a coefficient of restitution. If you want to try to figure out what that means, restitution is that part of the time they're in impact when you've seen high-speed pictures, I suppose, of a tennis racket hitting a ball or a golf club hitting a golf ball. The golf ball is deformed significantly, or the tennis racket squashes the tennis ball significantly. During part of the impact, it's crushing the ball, and during the other part of the impact, the ball is recovering and it's starting to move away from the racket or the golf club. Well, that part of the period of impact is called restitution, when it's being restored to its original configuration, and this coefficient of restitution relates the energy basically that's used to crush it to the energy that's recovered when it's restored. But the definition of the coefficient of restitution is this simple definition: the relative velocity in the normal direction to impact at time 2 is equal to minus e times the relative velocity at time 1. Now usually the relative velocity, well, they're different. Before the two objects are coming together, and we're talking about in the direction of the normal direction of the collision, so they're coming together, so the relative velocity, you might say, is negative. They're getting closer together, they're closing, and after they're moving apart, so one of these is positive and one of them is negative, hence the minus sign there, which then allows E to be a positive number. In the case of perfectly elastic collisions, which would be modeled pretty closely by two billiard balls or something like that, E is 1. If you drop a golf ball on a concrete floor from a height of 60 inches and it rebounds to 60 inches, then that is a perfectly elastic impact. And probably that golf ball isn't allowed by the Pro Golf Association, okay? If you drop it on the floor and it sticks to the floor, then you need a new golf ball for sure, because that's a perfectly plastic collision. It adheres together. Real values of E are somewhere in between. Okay? E is somewhere in the range of 0 to 1 for real collisions. 1 is the ideal case when they rebound with the same relative velocity in the normal direction, and 0 is the ideal case when they stick together. And we use that because we need an additional equation to be able to solve these problems. Here's an example of a golf ball. Let's suppose we have a golf ball, we drop it on a concrete surface, and we're given that E is 0.9. The question is, what's the height of rebound when you drop it from an initial height h? The approach to solve this problem has got 3 parts. We drop it from a height h, we have to find the velocity before impact. We'll use work energy to determine that. During collision with the floor, we're going to use impulse momentum. Okay? Well, in this case, it's simpler. We don't really have to apply the impulse momentum principle. All we have to do is use the definition of E to give us the velocity after impact in terms of velocity before impact. And then we'll use work energy again to determine the height of rebound. Okay, I'm skipping a bunch of steps, but if you calculate the velocity, and this equation I think may even be in the handbook, if you calculate the velocity of an object that falls a distance h by work energy, you find that the velocity before impact is 2g times h, the height you dropped it from. That's the initial velocity before impact. Velocity v2 is the velocity after impact. We use the definition of the coefficient of restitution to say that v2 is minus ev1, or e times 2gh. Well, I don't worry so much about the minus sign. Velocity v1 is down, velocity v2 is up. The magnitude is 2ghe, right? Okay, now I've got another problem between time 2 and time 3. Time 2 is just when it leaves the concrete floor on the way up, and time 3 is at the height of the peak of its rebound. So I'm going to calculate, I call it H2 here, I guess that'd be the height of the second bounce, but it's the height at time 3, if you like. H2 is, I'm using that equation right there, V over 2GH. I'm sorry, V over 2G. Or the velocity after impact is E times 2GH over 2G, or E times H. So this is an important observation, that E, the coefficient of restitution, tells you the percentage of the height of the rebound that ball is going to bounce back up. When the basketball official checks the basketball before the game, that's the way he tests it. He holds it at a certain height, and he drops it, and if it rebounds to a height that he recognizes as the proper height, then it's got the proper amount of air in it, and it's properly inflated for the game. So he's measuring E when he performs that test. Here's an example problem that uses the principle of impulse momentum. This is direct central impact. Now, what do we mean by direct central impact? This is the only kind of impact that I expect to be covered on the EIT. It means that the velocity of particle A and B are in the same direction before and after impact. So it's collinear, you might say. The two particles aren't coming in at different angles and going off at different angles. It's a much simpler situation. The relative velocity is just the difference in the two speeds, okay, before and after. We don't have to worry about motion in the normal and direction perpendicular to the normal. Okay, we got particle A, we got particle B. Particle A's got velocity v at VA sub 1 at time 1, and particle B's got velocity VB sub 1 at time 1. Notice that VA sub 1 better be bigger than VB sub 1 or there won't be an impact, right? This is what happens before impact. This is the situation after impact. Velocity of A is VA sub 2. Velocity of B is VB sub 2. Notice that VB sub 2's got a longer area than VA sub 2. I know that in advance, else A goes through B, and I know that can't happen, right? Now, I don't have to know those things, but they help me interpret the problem. I don't have to observe that VB2 is greater than VA2. Okay. For the system of A plus B, just as we said before, there is an impulse, but it's internal. The impulsive force is between the two particles during collision, and since it's internal, for the system, there's no external impulse. So linear momentum is conserved. The linear momentum P at time 2 is equal to the linear momentum P at time 1. Or the mass of particle A times the velocity of particle A at time 2 plus the mass of particle B times the velocity of particle B at time 2. And notice that everything's to the right here, so that the equations I'm going to derive, if maybe this one's moving to the left, would still apply, but I'd get a minus sign in my VB term. Okay? MAVA2 plus MBVB2, that's the linear momentum of the two particles. Notice that A's got a mass of 4,000 pounds. Now, I'm getting a little loose with my units. You see, I didn't put a G sub C under here, under here, under here, and under here, because mass occurs in every term. So I can have G sub C in every term, and I didn't bother to write it. But you notice that if you had an impulse out here, you wouldn't have a mass on this side. If there were an impulse, I'd have to be careful about what units I used, and I wouldn't be using pounds, I'd be using slugs. I'd calculate the mass of that 4,000-pound truck by dividing by 32.2, and 4,000 divided by 32.2 is 124.2, so its mass would be 124 slugs if I were working a problem where I had to be real careful with my units. Down here I don't have to be, so I'm just using 4,000 instead of dividing by 32.2. Okay, the units are going to cancel. The pound of mass are going to cancel out. At time 1, I have 4,000 times the known velocity, 44, okay, and 44 feet per second, and 2,000 pounds times the velocity, 20 feet per second. What we've got here is a truck, weighs 4,000 pounds, impacting a small car weighs 2,000 pounds. It's a rear-end collision. He's going 44 feet per second. What's that, 30 miles an hour? This little guy's going slower, or else they wouldn't have this problem. And we're going to look at what happens after impact. We're going to assume that we know that the coefficient of restitution is 0.2. That is to say, mostly plastic. They don't quite stick together, but they're far from elastic. You ever see two cars hit at, say, 30 miles an hour or a relative velocity of 10 or 20 miles an hour there? If you look at the back end of one and the front end of the other, you'll judge right away that it wasn't an elastic collision. An elastic collision would mean everything restores to its original configuration, and that is unfortunately not yet the case with most automobiles. They're going to be plastically deformed. That's why this number is not 1 in this case. But we have to be given that here. Okay, here's my equation for VA and VB2, the unknowns. I got two unknowns, I got one equation. That's why I need another piece of information. That's why I need E. I have to have the definition of the coefficient of restitution. I have one equation that comes from impulse momentum. The coefficient of restitution tells me this. It tells me the relative velocity after is equal to minus E times the relative velocity before. Well, I've written the minus sign in a funny way here. B minus A minus B. I've written this as a positive relative velocity. I know A is going to be bigger than B after, and I know B is going to be bigger than A before, so I've sort of incorporated the minus sign in the way I wrote the relative velocity terms. Or the difference in velocities, VB2 minus VA2, is E times 44 feet per second minus 24 feet per second, or 0.2 times 24, or 4.8 feet per second. Okay? It says that VB2 after collision is going 4.8 feet per second faster than VA2. So the pickup gets shoved out ahead of the car, the little particle, gets shoved out ahead of the pickup at a faster rate than the pickup after the collision. So we plug this equation into our equation for impulse momentum, or conservation of linear momentum, and we come up with, let's see, I don't know if I read you that one. Let's look at the previous page here just a minute. This right-hand side, we can compute. Everything on there is known. The right-hand side comes up to 216,000 pounds feet per second, right? So that's this 216,000 pounds feet per second. Pounds feet per second. Everything's got the same units. I bring the 2,000 times 4.8 over here. That's 9,600. And I get VA2 times the mass of one plus the mass of the other is 206,400. If I divide by mass, the mass goes away and everything's left is got velocity units. I'd observe that the final velocity of A is 34.4 feet per second. That's to the right. The final velocity of B is 4.8 feet per second faster, 39.2 to the right. And that's the final condition, right after impact. You might ask the question, and I think we're probably going to have time to do that. You might ask the question, how much energy is lost in that collision? Just before impact and just after impact, we know the velocities of the two particles, so we could calculate the kinetic energy before and the kinetic energy after. And you'll find that if you do that, maybe I'll have time in a minute, you'll find that there's a significant amount of kinetic energy that's lost. Where does that kinetic energy go? Well, it goes into deforming sheet metal on the car and the frame, and maybe on the backs of the people driving the car. It damages things. It's energy that's dissipated in the collision. Here is, looking at the same problem, here is a calculation of the impulsive force. Since I know the change in linear momentum, okay, of car A, now I'm restricting my investigation just to one car. That's the pickup, right? So I know the car A, during collision, has a force on it, F, that's a function of time, right? And that force, integrated with time, the area under that curve is the integral with time, is the impulse. So the impulse is that area. And that impulse is equal to the change in linear momentum of car A. Okay? Now you notice I haven't shown gravity, and I haven't shown aerodynamic resistance, and all the other forces that act. The only forces in the horizontal direction that might be important would probably be aerodynamic resistance, and maybe his brakes, and maybe, hopefully he's on the brakes, and maybe drag, from bearings and things like that. But those things are all going to be pretty small compared to the forces required to deform the front end of the car, the force due to this impulse. If that weren't the case, then just driving down the road at 44 miles an hour would deform the front end of the car, and we know that doesn't happen. So the impulsive forces are going to dominate the behavior of the car during this short period of time. How long does it take for the collision? Now, if you're involved in an automobile accident, it takes several seconds. The car, but that time involves the impact and then the car sliding to rest afterwards. But the impact itself is a fraction of a second. I've said here, for purposes of making our calculation, that it's 200 milliseconds, or 0.2 of a second. So this is some relatively small fraction of a second, say 0.2 seconds. All right. Here, I didn't forget my units. I took the 4,000 pound mass of the car, 4,000 pound really it's a weight of 4,000 pounds, and I divided by G, so that the mass is W over G, right, in slugs. 4,000 pounds over 32.2. Now, I never actually wrote slugs, but that's the mass in slugs, times the final velocity minus the initial velocity. Notice that the final velocity in the x direction, okay, this is the x direction, is less than the initial velocity. So the impulse must be negative. The impulse is minus 1,193 pound-seconds. It's got units of force times time. It's a negative and it's in the I direction. If we estimate the duration of the impact, not the whole accident, but the impact to be about 0.2 seconds, then we can calculate the average value of this force. It may really do something like that, okay? And we aren't going to calculate the peak value, we're going to calculate the average value, all right? The average value is average force times the time of that we're averaging over, the time of collision, or 0.2 of a second. Or F average is I, the impulse, over delta T. So the average value of the force is about 5,962 pounds in the I direction. Negatives, because it's to the left. Okay, here's another little problem of an automobile, and let's see what we can learn from it. This is problem 16 on page 17-7. We're given a 3,500 kilogram car, and that's a pretty big car, right? 7,000 pounds, so that's a Suburban full of the whole bridge club. Travels at 65 kilometers per hour, and he skids. Mu is equal to 0.6. That's a reasonable number. He skids for 3 seconds and hits a wall. Find the velocity of impact. Well, there's a clue here. He tells you that the force of friction is applied for a known time, 3 seconds. And that's a clue that says impulse momentum is a useful tool, because you know friction times time is going to give you an impulse. So you can calculate the impulse and therefore the change in momentum. If he said he skids for 100 yards or 100 feet, then you would be able to calculate the work, and you'd use work energy to calculate the change in kinetic energy. So look for clues that tell you how the best approach, to work these problems. Here's a free body diagram. We got a car, we got the weight, we got normal force. If it's traveling on a horizontal surface, and he's not traveling through like a roller coaster through a curve, then there's no acceleration in the direction perpendicular to the surface. Therefore, some of the forces in the vertical direction, the y direction, is 0. Therefore, N is equal to W. So I know those two forces. They're not important to me. What's important is the forces in the horizontal direction. Since he's skidding, I know F is equal to mu N. Okay? Now, up until the time that he starts to skid, You know, he might be putting the brakes on. The friction force builds up and builds up, but until he skids, the forces might be less than mu n. But after he starts skidding, force is equal to mu n, and we'd be using the kinetic coefficient of friction because we know he's sliding, and they give us that up there. They don't say which one it is, they just tell you which one to use. But if they give you a static coefficient and a kinetic coefficient of friction, in this case, we'd be using the kinetic coefficient. Well, because he's skidding. Incidentally, what is a good driving skill tells you that if you get on your brakes and you lock your wheels up, not only do you not have so much control of the car, but you don't have as good a braking action as you do if your wheels are still turning. And that's because you're invoking the kinetic coefficient of friction as opposed to the kinetic coefficient of friction as opposed to the static. Remember, the static coefficient of friction is a little higher. So if you operate your brakes in the optimal way, the wheels they're still turning, they're not slipping, they're just at the verge of slipping, you can get frictional braking forces that are higher by the ratio of mu static to mu kinetic. So maybe you get 70% instead of 60% of your normal force on those wheels as braking action. And that's one reason you try not to lock your wheels up. And that's why anti-skid brakes are, well, the more important reason is you have better control if your wheels aren't locked up, but you do have better braking action. All right, we got this clue that says use impulse momentum because they tell me the force is applied for a certain period of time. And we know the force is mu n, mu times the weight. So the impulse is what I want to calculate. First of all, the weight. Since they give me the mass, I need to calculate the weight. Weight is equal to mg. 3,500 3,500 kilograms times 9.81 meters per second squared is 34,335 newtons, or 34 kilonewtons. Okay, that's the weight. The norm from equilibrium in the vertical direction, the normal force is equal to W, and the law of Coulomb friction says F is equal to mu times N, which is mu times W, or 60% of the weight, 20,601 newtons. Okay? So I've got this 20 kilonewton force that acts to the left, okay, in the negative x direction, for a period of time 3 seconds. So the integral of F dt, the vector impulse, is minus, that's a minus sign there, kind of hard to read, minus 20,601 newtons, okay, times 3 seconds in the I direction. So I've got a impulse that's negative 61,800 newton seconds in the I direction. Left off my minus sign. Better put it in there. Okay. That's the impulse. Therefore, the momentum of the car, which is originally in the positive x direction, is going to be reduced by this much right here. Let's write that equation. Okay. The impulse momentum says the impulse, which we just calculated, is equal to the change in kinetic energy. I'm sorry. It's been a long lecture. The change in momentum. The impulse is negative, implies that the momentum is going to be reduced. P2 minus P1 is going to be negative in the x direction. mv2 minus mv1. The time 2 is just before he impacts the wall. That's what they're asking me to find. I guess I ought to make these things vectors to make my equation all vectors. And v1 is the velocity when he starts his skid, when it's given, and it's given to be 65 kilometers per hour. Okay? So, I'm going to solve for mv2. mv2 is equal to impulse plus mv1. So I've got the initial momentum plus the impulse is equal to the final momentum. 3,500 is my mass in kilograms times v2 is equal to the impulse I just calculated minus 61,803 in the I direction, okay, plus mass, and why I wrote mass there I don't know, but here's the velocity, 65 kilometers or 65,000 meters in 1 hour or 3,600 seconds, so it's 1,800 meters per second. I didn't write mass because I knew I was going to divide by it. I divide the mass of 3,500 kilograms, and that gets rid of that term and puts a 3,500 kilogram here, and I've got the velocity. Velocity at time 2 is the impulse divided by mass plus 18 meters per second in the I direction. That's the initial velocity. This is the impulse. It's in the negative x direction. It's going to reduce that. So I have an 18 meter per second velocity reduced by 17.65. So he nearly gets stopped. He's left with a V2 of 0.4 meters per second in the I direction before he hits the wall. Since they gave me velocity in kilometers per hour, I went ahead and converted. I don't know which they would want your answer back in, but if you convert back to kilometers per hour, you get like 1.43 kilometers per hour. So he's nearly at rest, and he probably didn't total his car, but he sure does some damage, depending on the nature of the wall, I guess. Okay, free vibration. There's a section in the review that indicates that you might have some questions on one class of dynamics or one class of vibrations, and that is free vibrations. Systems, any mechanical system that leads you to a differential equation like this is a system that experiences free vibration. Basically, what is free vibration? It means that the oscillation, once set in motion, will continue. There's no damping. If you have a mass and a spring like this, and it's in a vacuum, so there's no aerodynamic resistance, and they got a perfect spring, you pull it down an inch, and you let it go, it's going to continue to oscillate at an amplitude of 1 inch forever. There's no loss. Of course, in reality, there's always some loss. But if the damping is low, this differential equation will govern the motion for a significant period of time, and that's why it's important. Now, if you see a differential equation like that, you will know the solution to it down here. But let's go over how you get that, how you might get that differential equation, and how you could obtain its solution. Consider a lumped mass of magnitude m and a spring with constant k, and the mass is suspended from the spring. It's a little more complicated if you include gravity. You could have this thing on an air table, right, and then you wouldn't have gravity in there, and it'd be a little simpler problem. But I've gone ahead and included the effects of gravity, and it might stimulate you to review your differential equation solutions a little bit, but let's see what it leads to. Here's a free body diagram. Simple enough, but remember, always draw a free body diagram for your own use. The problems that you're most likely to muck up are problems that are so simple you don't need a free body diagram, right? Because in fact they aren't. You will probably need it when you don't draw it. So good practice to always draw the free body diagram. This one says that if it's displaced a distance x, there's a restoring force in the spring that points up if x is down. If it's pulled down, the spring tension pulls it back up. The magnitude of the force in the spring is always kx. That's the definition of a linear spring. The weight acts, and that's the only other force that acts. It's downward. So we have Newton's second law, which says the summation of the forces is equal to the mass times acceleration. I've written it in scalar form here because I'm only interested in the vertical direction. In this case, that's the x direction. Applying Newton's second law in the downward direction, I get, in the downward direction, I have a minus kx is that force, plus mg is equal to mass times acceleration, mx double dot. Or, lumping the mx double dot and x over here to get my differential equation, I have mx double dot plus kx, really I guess I put the kx over there, is equal to the weight, or mg. If I divide by mass, I get x double dot plus k over m times x is equal to g. Well, this isn't exactly in the form of this equation up here, is it? The right-hand side's not 0. Well, that just means that the solution has two parts. If you remember from your differential equations, there's a homogeneous part, which is this same equation with the right-hand side 0, and there's a particular solution that satisfies the right-hand side. Notice it's easy to tell what the particular solution is. If x is a constant, then this term is 0. And what constant value would x be to satisfy this equation? Well, it'd be gm over k, right? Or w over k. What's w over k? The static deflection. If you know the weight and you hang it on a spring of known stiffness, you're going to deflect a known amount, which you'd calculate to be w over k. So a static solution when there's no acceleration is x is equal to w over k. That's a special case. The dynamics, though, comes from this problem. So if we look at solutions to this problem, the homogeneous part, we'll have, a case of free vibration because it obeys that differential equation. Where, in our case, notice that this parameter here, omega squared, is k over m. It's the same differential equation as that, with omega equal to the square root of k over m. The natural frequency of a mass suspended by a spring is the square root of k over m. If you work out a torsional vibration problem, you'll get a similar term here that'll have the same units. It just has different. It'll have different parameters in the frequency. This is the natural frequency or undamped frequency of vibration. It's the frequency. It's got units of radians per second. Okay. Not degrees per second, not RPMs, but radians per second. And it tells you the frequency at which this motion will occur. Solutions to the homogeneous part, the part with the 0 right-hand side, the equation of a free vibration, are like this, of this form. X of t is C1 times a cosine of the natural frequency, omega, times time, plus C2 times a sine of natural frequency, omega, times time. Notice you got these two constants in here. We'll talk about how you might get those in a moment. The total solution is the particular solution, which was the static deflection, plus the homogeneous part, which is this part up here. And graphically, this is what that says. This says that if this distance right here, x, w over k, is the static deflection, then the oscillator is going to oscillate about that static position with some frequency, omega, okay, equal to k over m. And since it's free vibration, the amplitude of each of these peaks is going to be exactly the same. There's not going to be any damping. If there is damping, of course, in a system, you see vibration that does something like this. Amplitude diminishes with time. Well, that's not, apparently, from what I see in the review, that's not going to be covered on the manual. On the exam, you're only responsible for understanding free vibration. If x is measured instead from the static equilibrium position, in other words, if we had done this on an air table and looked at horizontal vibrations, or if we had measured x from the equilibrium position, we would have, instead of having the homogeneous part equal to that, we'd have the solution be equal to that, because the equilibrium position, the static deflection would be 0 then. And so that's how you'd set up an equation and obtain and apply the solution, or get the general solution for the free vibration. Let's take a little. Okay, let's consider an example problem of free vibration. Suppose we have a mine elevator, which basically would be a mass at the end of a long pulley, a long cable. Suppose the cable is 1,000 meters long, so it is a long cable. Deep mine. Cab has mass 4,000 kilograms. Got to carry lots of people. When the cab is initially installed on the cable, so they spool the cable out for some reason. They got the cab in the bottom, and they let it hang down there, and they hook the cab on it, and they observe that it deflects 1.5 meters. And mine health officer comes to you and says, I need to know what the expected natural frequency of vibration of the cab is, because certain natural frequencies tend to make your miner sick, give you an upset stomach. And that's the challenge here. Let's see if we can do it. The weight of the elevator would be mass times G, which is 39,000 newtons. K, that cable serves as a linear spring, is, I wrote it upside down, so I had to put the minus sign there to correct. It's 39,000 newtons over 1.5 meters, or 26,000 newtons per meter. That's the equivalent spring constant for that cable. So omega is the square root of K over M. Well, 26,000 over 4,000 under the radical is 2.56 radians per second. And that may not mean much to you, but if you want to compute the period, for example, of one cycle, you'd say 2 pi over omega, 2 pi radians per cycle, right? Times omega in radians per second, so we're going to have seconds per cycle. That's the period. 2 pi seconds in each cycle is 2.45, so about 2.5 seconds in a cycle. And industrial engineers will tell you that for vibrations in a certain range, and I don't know if this happens to be in that range, but vibrations in a certain range are very uncomfortable, and this might be one of those. It would also be important to know if there's some other equipment, maybe the mechanism that starts the lift of the cable, if it excites, if it's applied in such a way that it excites this natural frequency, then you're going to have forced vibration. You're going to have large amplitudes and obviously a dangerous situation. So it's important to be able to calculate the period of free vibration. That's just one example. All right, let's look quickly at what we've done in the last 3 hours. We looked at Newton's second law, the fundamental basis of dynamics, which says the summation of the forces is the mass times acceleration. For a rigid body, we always write the acceleration of the mass center G. For a particle, it doesn't matter. Summation of forces is mass times acceleration. All points have the same acceleration. For a rigid body, since it has angular motion also, we also have an angular equation of equilibrium, of motion. I haven't written vector signs on here. This can be a vector equation too, but in two-dimensional rigid body dynamics, this scalar equation is enough. And it says the summation of moments about point G is equal to I about point G times alpha. How many unknowns we have in these two equations? This one in 2 dimensions has an x and a y component, and this one has one a z component. So there's 3 unknown acceleration terms. If you know all the forces, you can calculate the 3 unknown accelerations: ax, ay for point G, and alpha. And you know then from kinematics you can calculate the rest of the motion of the rigid body. Remember, there's sometimes an advantageous shortcut. If there is a point O on the body that has 0 acceleration, and maybe we better restrict it for your purposes to a point that's pinned. If there's a pinned point on the body, you can write about that point O, the summation of moments about point O is I about point O alpha, and often this will uncouple from this equation. Maybe this is the only one you need to write. Whereas otherwise you might have to write these 3 scalar equations instead of this one. So this is a useful tool. You can't write summation of moments about any general point is equal to I about that point alpha. It simply isn't true. But for a pinned point, you can do this. You have to use the parallel axis theorem to compute moments of inertia about other points. Remember how to do that. You're given IG for various common shapes in the notes. We also looked at 2 other methods. I'm emphasizing here that one of them is a scalar method, work energy, no vector signs there, and one of them is a vector method, impulse momentum. The work energy principle says that the work that's done on a system, which could be a particle, could be a rigid body, could be a group of particles or rigid bodies, the work that's done between configuration 1 and 2, or time 1 and time 2, or position 1 and position 2, whatever you want to think of those, is equal to the change in kinetic energy between those two positions. So you have to know how to calculate the kinetic energy for a particle, which is 1/2 mv squared, or for a rigid body, which is 1/2 mvg squared plus 1/2 I about g omega squared. Okay? Special case for particle, there's no omega, and v can be v of any point because it's all the same. You also have to know some kinematics sometimes you have to be able to relate omega and v sub g, and that's kinematics. Time 1 and time 2, very commonly it starts from rest, in which case there's zero kinetic energy here, or it winds up at rest like our tire did when it got to the top of the hill. The kinetic energy too is zero. We talked about the conservation of mechanical energy. My preference is to always apply this. You saw I got in trouble with a sign on the conservation of mechanical energy, on the relationship between work and potential energy. The sign issue is much easier to handle here. It's much easier to remember. This is a very simple principle. You can always apply it. I prefer to apply this always in preference to the conservation of mechanical energy, which is not a general principle, but only applies in certain cases, especially when there's no frictional work. Impulse momentum says that the impulse on a free body, or a system of free bodies, is equal to the change in momentum. Now I should write P2 and P1, I guess, like I did before, and we have to remember how to calculate P. P is 1/2 mv sub g squared. It's v for a particle, or 1/2 mv sub g squared for a rigid body. Okay? That's the linear momentum, and I need arrows over those. Squared. Thank you. Okay? You heard the joke about how the college professor referred the question to his chauffeur when it was too complicated. He said, I can refer it to my cameraman here. He says I need a squared there. Okay? Impulse momentum. Remember to draw free body diagrams, especially when you're doing this. You got to have a free body diagram, or you can't write those equations. You'll overlook something. So draw free body diagrams. Okay. Remember, there are certain clues that tell you which coordinate systems are most useful to you. It's never the case that you have to use one coordinate system, but it's usually the case that one coordinate system makes the problem much simpler than others. So think about what coordinate system set the problem up in. There are clues that tell you that. There are clues that tell you whether you're going to use N2L. What's that mean? Newton's second law, right? Whether you're going to use this approach, or whether you're going to use this approach, or whether you're going to use this approach. Those are pretty important clues. Let's go over some of them. If the problem says, calculate the acceleration, okay, in any shape, form, or fashion, they're probably telling you to use Newton's second law. If the problem says find the final velocity, then they're telling you probably one of these two things. Whether he says linear velocity v or angular velocity omega, he's probably telling you to use one of those two things. If he says the forces that act over a known distance, then he's telling you how to calculate work, and he's suggesting that you'll have better luck using work energy. If he tells you the forces that act for a certain period of time, the rocket burns for 2.5 seconds on the thruster, then he's telling you know the impulse and you should use impulse momentum. So remember the clues. They tell you a lot about the most productive way to attack the problem. And I guess I will be we'll be scheduling a time for you to get back to me with questions, and I'll look forward to that. I have had a little trouble looking deep into your eyes during this tape and figuring out if you're following me or not. It's hard to do, so I haven't done that. I hope that I've approached the subject, the review, at the proper